I want to go ahead and get started with our first guest tonight. I am so honored to have her here. Our first guest is Dr. Penny Boston. On an average day, Dr. Boston goes to the office underground in a dark void that could be extremely hot or extremely cold, filled with poisonous atmospheres of carbon monoxide and ammonia with sulfuric acid-filled walls and hot acid water. She believes the best place, we're going to be talking about not only caverns on Earth, but of course we're going to be talking about training missions and human missions to Mars. She believes the best place to find life on Mars will be underground, not in the cold radiation-blasted deserts of the surface. As a TED lecturer and author of 133 publications, and most recently the star of National Geographic's Into the Lost Crystal Caves, Dr. Boston is the director of Cave and Karst Studies and professor of Earth and Environmental Sciences at New Mexico Tech. This is going to be an interesting interview. Let's go ahead and bring her on. Penny, good evening. I did it again. I hit the button a little bit too quick, but I did give her a little heads up. Hopefully she'll call us right back. She works with, until she calls us right back, she works with many groups like the NASA Goddard Space Flight Center and NASA Jet Propulsion Laboratory. She probes the intimate connection between Earth's most challenging places and exploration of our universe. So we're going to be talking a little bit about Mars Explorers, the national, just all kinds of stuff. We will get her right back. Penny, I'm sorry. I told you that could happen. Good evening. Welcome to K-Talk and the Fringe Radio Show.
Not a problem. I'm still here. Hi.
How are you? It's an honor to have you here.
Well, it's fun, and thanks for the invitation. I always love to talk about the stuff I do, so I welcome the opportunity to chat with you and your listeners.
Well, you do quite a bit. I came across you about a year ago watching some of the TED Talk stuff. And that's why, again, I know you're a very, very busy person with a lot going on, but I thought I got to do whatever I can do to get her on the show because your work is absolutely amazing, and it covers so much. And as I put notes together for the show and got people that sent in questions, it just kind of ballooned out. So I would just like to kind of, I don't have nothing scripted, but there's just so many things I'd like to talk about and things that we'd like to hear from you. How did you get into all of this? How did your interest get you into playing around with caves?
Yeah, well, I didn't start out as a recreational caver. I think a lot of folks that wind up in somewhere to do with cave science, did it for fun as kids and young people, but I didn't actually. It was really the science that sucked me in. So, I've been interested, of course, in life on other planets and life here on Earth and life here on Earth in the past. Really, since I was a little kid, I was a science geekazoid kid, and so I always wanted to climb into a rocket ship and go zip around the galaxy and look for cool, weird life forms, And unfortunately, the rocket end of things has not panned out as well as I would have hoped by now.
Not yet.
No, not yet. So a lot of my science career has been focused on extreme environments, and the first extreme environments I worked on, early in my career were hot and cold deserts, polar environments, salty environments, acid environments, and so forth on the surface. But in the early 1990s, with a couple of colleagues from NASA and Russia, published a paper suggesting that the last best place to look for actually living microorganisms on Mars would be in the subsurface. And so that got us looking at caves because it was a heck of a lot cheaper, we thought, to go into caves than it would be to, have a giant drill rig and so forth. And we didn't have any funding for it. So,
right.
And then when I started caving, I realized that what we were really experiencing was as if we had all these little planetlets right under our feet. So the subsurface is so tremendously different from the surface of Earth that it really is a whole lot of very exotic, in many cases partitioned from each other environments. And so each one of those was a test case that I could study. And I also realized that a lot of other people were creeped out by going in caves. And so there wasn't a whole lot of competition. So, in that regard, it was kind of an open field. So all of those things really latched on to my imagination, and I have been doing that, ever since for the last almost 25 years now.
Wow. A question that I had, and actually the listeners sent in some questions, but I'll wrap it all up into one. In the first line of your bio, you talk about going into these caves that have poisonous atmospheres, and they have carbon monoxide, ammonia, sulfuric acid. Just as kind of a general statement, I have never got into caving. I find it fascinating. The only time I've been in a cave was years ago when I was a real young kid. I went to Mammoth Cave in Kentucky. That was about the size of it. I just remember it was about 105 degrees outside, and when we went into this thing, on a guided tour, it was freezing in there. But it's just a general statement, especially here in Utah. There are a lot of caves. There are a lot of openings that go down into the ground. I would assume that one needs to be quite careful because you could encounter things there that could take your life.
Well, this is right. And in fact, several years ago, you actually had a cave mortality. You had an accident occur in your state. So caves are wonderful places, and people can learn to cave safely, but you can certainly get severely injured or killed in a cave environment if you don't know what you're doing or if you're foolish enough to go in by yourself. So, for people who are interested in it, I would recommend seeking out your local cave grotto. These are this is what we call cave clubs that are associated with the National Speleological Society here in the United States. Of course, there are cave clubs throughout Europe and so forth. So wherever you live, you can find like-minded folks. And cavers are very generous people, by and large, and happy to share what they know about caving safely and going into caves. So, you can pursue it safely, but it's nothing to take lightly and nothing to joke about, especially some of the more extreme condition caves that we are seeking.
Now, with the caves that you're looking in, do they like here in Salt Lake City, not here right downtown, but in these mountains and stuff like that? Are the extreme environments there?
Oh, absolutely. Even what seems like a benign or non-extreme cave environment is very extreme from several points of view. So, if you are an organism of any type, either a microbe or a small invertebrate or even a vertebrate, there is very little to eat. So on our planet, as we know, food is made by plants and algae and cyanobacteria from sunlight energy, and that enables those kinds of cells to glue carbon together and various other atoms and make the stuff of which we're all made and which we eat for food. So if you're in a cave environment, what you get for energy is either sort of the leftover bits that finally make their way into a cave, so the nutrient base is really low, or you're the kind of exotic microbe that I'm very interested in, and these guys actually make their living not by eating the kind of food that we understand and eat ourselves, but the transformation chemically of non-organic materials, and they get their life energy out of that. So they're pretty different life forms, and we call them chemotrophs, which just means chemistry eaters, basically, and they can use mineral compounds in the rocks and so forth, and they transform those materials. So, from the point of view of just finding stuff to eat and energy sources to run your life as an organism in a cave, it's an extreme environment.
I can see that. Does it get pretty warm and pretty cold in these deep caverns?
Well, one of the amazing things about caves is because they are sort of insulated, because they're made out of some kind of bedrock material, the temperature within any cave is usually pretty constant. This is one of the actual benign and protective aspects of being in a cave. But the temperatures that you find caves containing range all the way from exceedingly hot to freezing and below freezing. And that depends on what the altitude of the cave is. It depends on what the latitude of the cave is. If it's in a high latitude in Siberia, it's going to be a cold cave. If it's in the tropics, it's likely to be a much warmer cave. But there are also complexities depending on the exact geometric shape of the cave that can modify how warm or cold it is. If the cave is in proximity to an unusually hot source, like an upwelling magma body or something like that, it can be really hot. So one of the nice things about studying caves is that you can kind of pick a cave within any temperature regime that you are interested in studying.
And some of those, well, from what you're, again, just obviously some of them can be quite extreme, quite extreme environment.
Oh, sure, yeah. We have worked in caves at all different temperatures, and we've worked in caves with all different kinds of, poisonous to us kinds of gases and geochemistry, but certainly not poisonous, and actually home sweet home to the organisms that are actually living there. And the reason that we go there is not just to be daredevils for no purpose, but because this is the kind of place that we want to see how far life on Earth has stretched itself in being able to not only tolerate extreme environments, but to actually thrive and as a matter of fact, to prefer what we would consider extreme environments, but are not extreme to them.
Now, it's interesting, Penny, we always talk about, hear about trying to find life elsewhere, and yet, our oceans we've just barely, we've barely scratched the surface. I know the filmmaker James Cameron just funded his own, I know there's a movie that just came out, he funded his own a deep sea exploring type sub that I think it dove to like 37,000 feet. We've got, underground caves in these oceans, and here, with the type of exploration you do, have you encountered different? Have you come across different life forms, whether that may just be micro, like amoeba type life forms or plant life forms? Have you been able to catalog or view or see new things in these caves that nobody else has seen before?
Yeah, as a matter of fact, virtually everything we see in the most extreme caves are novel to science. So, for example, the giant crystal caves in Nika in Mexico that are so extremely hot, where we have to, use the ice suits. We're packed in ice vests, and we've got ice packs under our caving helmets, and we're breathing cooled air coming across ice cylinders, with backpacks on our backs. Those microbes, we are sequencing their DNA and looking for their closest relatives, because we can't get any closer than their closest relatives because none of them have ever been seen by science. And this is very typical of subsurface environments. Now, there are some microbes in, somewhat less extreme caves that are related to the microbes in the soils above and things like that. But the more extreme the temperatures and the chemical conditions become, the less and less likely those organisms are to be closely related at all to anything that anyone has ever studied. So really what we're learning, and what people who are studying the seafloor subsurface are learning, is that the subsurface biosphere, as you might consider it, is actually far, 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 far more biodiverse than all of the biodiversity on the surface. Now, it's microbial biodiversity for the most part, although there are invertebrates that make their living in caves, and there are, a certain number of vertebrates that live in caves, but this huge amount of biodiversity and chemical diversity, organisms that can do all sorts of amazing chemical transformations, that's where the biosphere shows its chops,
right,
about what it can do, using chromium compounds for energy, pooping out manganese minerals. All these, amazing things that certainly we on the surface, our kind of life, certainly can't do. So they really are almost entirely novel.
Very interesting. We get a lot of students that listen to us up at the University of Utah, and Tanya writes in and she says, Dr. Boston, in your cave exploring over the years, have you come across any types of precious metals, diamond-like material, or things out of the ordinary?
One of the amazing things about caves is that they really are mineralogical factories. And part of the reason for this is that in a lot of them, it brings together all three phases of matter. So, you get fluids, and you get the solid rock materials and minerals that are there, and in many cases you get interaction with, atmosphere, and sometimes those atmospheres are chemically quite different from the above-ground air. And so you have this tremendous range of chemistry that's possible. And you also have, temperature extremes. And all of those things seem to come together and produce a wide array of minerals that are either unique to caves or very unusual in general and are found in caves. And the other ingredient into this that I'm particularly interested in is the fact that microorganisms themselves help to trigger a lot of mineral formation. And so, diamonds, no. Diamonds are produced by very high temperature and pressure conditions quite deep within the surface of the earth, beneath the surface of the earth. So those kinds of minerals would not be made. But certainly the lower temperature things like copper and gold and rare earth elements and manganese and iron, these are often placed into rock fractures by upwelling fluids, and the microorganisms have a lot to do with that. So beautiful secondary cave mineral decorations are really very commonplace in a lot of caves, and form a whole area of study. Paolo Forti is an Italian mineralogist who studies exclusively cave minerals, for example, and traveled all over the world to study these kinds of things. Bogdan Onak, who is a Romanian mineralogist who studies caves and now is at the University of South Florida in Florida, studies these. So there are quite a few people around the world whose life work is really centered around these remarkable materials that we find in caves.
Well, maybe someday when you're down there hiking around, is it like the Lost Dutchman cave where they said the gold veins were so thick you could chop it off?
Right.
I'm sure you keep.
Maybe I'll get rich.
I'm sure you keep your eyes open, because there's got to be some unique things. One of our listeners from Boston, the Boston area, writes in and says, Dr. Boston, do you have any thoughts on the plankton-like material found on the exterior of the International Space Station?
Well, I do. I actually have a lot of thoughts about microbes in these extreme environments. I mean, we certainly know that microbes contain members that are extremely radiation resistant and that are extremely desiccation resistant and that can tolerate high intensities of very short wavelengths, ultraviolet. And so the ability for some microbe or other to infest almost anything within reason is out there. We certainly know that over the history of human space flight, particularly in vehicles that are on orbit for a long time, like Space Station, and the now no longer in orbit, but the Russian Mir space station that was in orbit for so many years, that they had many, many problems with microbial contamination because the microbes are just incredibly resourceful at finding ways of eking out a living in ways that our kind of life, has a hard time doing. So one other end of the spectrum of my interests, besides, intrinsic life forms that you would find on other planets, is the microbial environment for human constructs on orbit or on other planets, these closed environments where humans and their life support organisms are going to be functioning, and how one controls and, in fact, uses to one's benefit, the bioflora that are a natural accompaniment of all of us. We certainly know now that we ourselves, each one of us, is really more of an ecosystem than we are an individual. So for every one of your own personal cells, there are 10 bacteria and archaea that are living on you and in you. And these are not pathogens. They're not bad for you. In fact, quite the reverse. You would be much, much, much less healthy if you didn't have them. So they perform all sorts of ecosystem functions for us that we are just beginning to understand. And so we ourselves, have to be accompanied by our little packet of the microbial bioflora. Right. And so this is essential to us. And, of course, we're going to have to take those with us into space. And the potential then exists for those to get out of balance, because going into a completely new environment means we're going to have to learn, I think, how to do medicine over again. But I think that medicine itself here on Earth is beginning to move in that direction.
You want to take a couple calls?
Sure, happy to do it.
All right, let's see what we get. Caller, good evening. Welcome to K-Talk. You're on with Dr. Penny Boston.
Penny, how are you tonight?
I'm great. Thanks.
Have you ever been to a place called the Lost Sea? It's off Interstate 75, off Tennessee and Georgia border.
No, I don't think I have.
It goes down, I think, about 500 feet, and it's filled with blind cave catfish. They don't have any eyes.
Oh, very cool. Very cool.
It's called the Lost Sea. It's on the Tennessee
What's it called, Lost Sea?
Yes.
Huh. I should make a note of that. I have a friend and colleague, Derek Ford, who is a Canadian cave scientist, and he's well into his 80s now, and he's been in about 3,000 caves, and I haven't been anywhere near that many caves. I have a lot to go before I can challenge him for numbers of caves. But I love the higher life forms in caves, even though I don't personally study them. I adore them. So that's a wonderful tip.
It's constantly 72 degrees.
72, yes, yes. And of course, I have colleagues who study cavefish.
Their catfish are probably about 1.5 feet long.
Are they really? Wow.
And they have no eyes.
Yes, right. They don't need them.
Yeah.
Nothing to see. Wow, that's really big for a cave vertebrate like a fish. Yeah. There must be quite a lot of food coming into that cave for them, or maybe they're grazing on these chemoless microbes. I don't know, because catfish are scrapers, right, of algae and so forth on the surface. So perhaps they're living off the microbial growth on the walls of their cave.
Okay, well, thank you.
That's an enormous size.
No problem. Thanks for calling in.
Thanks.
Let me ask you, Penny, that's a question that somebody sent in, and a question I had is, it seems like a lot of these caves, obviously not the ones that are right near the surface necessarily, and maybe I'm wrong on this, but the ones that can, like that gentleman said, these caves that can maintain a constant temperature no matter what time of the year, do they essentially create their own atmosphere, if you will, or their own system?
Absolutely. There's a whole branch of study, although there's literally maybe not even 20 people in the world studying it. We've done some of this work. Micrometeorology in caves. It is a very subtle kind of meteorology compared to what we experience on the surface, where you have big, high and low pressure systems, storms and all that stuff, high winds and turbulent features and so forth. But in caves, everything is very much more subtle, and yet it's absolutely vital to both the mineralogy that occurs in the caves and also the biology that occurs in caves. And so the precise nature of what gases are in the atmosphere have to do with a lot of things. To do with any individual cave, sometimes they have very high carbon dioxide. Sometimes they have very high contents of things like hydrogen sulfide. Sometimes they have depleted lower levels of oxygen and so forth. So there's all sorts of variability in the interior environment. We also know that even just the geothermal heat of the Earth itself, as it is transmitted from the deep parts of the planet out to the crust, actually drives big convection cells in caves all by itself. And we know that rock material that sticks up acts like hot fingers, or stalactites, for example, that hang down into a cave act as cold fingers. So that interior weather system that caves have is something that we're only really beginning to start studying in detail now, and it's really critical for us to understand that, to understand where and how the life forms in caves are actually making their homes.
Wow. You know, these like, now he was talking about the catfish with no eyes, and obviously, I mean, they're, you know, in the deep depths of the ocean, and obviously in these caves, creatures. Do you believe that they evolved? Do you believe that catfish, if you will, physically evolved to where it doesn't have eyes because it's in an environment that's so dark? Do you think that?
Sure. Yeah.
Do they transform pretty quickly too, Penny?
Well, you know, we don't really know the speed with which an organism adapts to an environment like that. But I think that it probably is relatively quickly, because there are a couple of really important factors. So, you know, energy is everything, right? Energy is everything to us as humans. It's everything to the biosphere, the way organisms live and make their living. It's access to energy by way of food and nutrients or other energy sources. And so when you are in a cave, like I said before, you have much less access to food. So if you're an animal like the catfish that this gentleman mentioned, you have to make a living in a very difficult environment. So anything that allows you to dump something that requires energy for you to make it is going to be favorable.
Yeah.
So that's what's known as an evolutionary driver. You know, anything in the environment that helps favor animals changing, or plants, or any kind of life. But in this case, of course, we're talking about animals. So, I mean, the things that we know that cave animals do to adapt themselves to the subsurface include the loss of eyes, because it doesn't matter if you don't have them.
Right.
So if you get mutations that cause you to not have eyes, maybe it's actually a good thing. Maybe you're even saving energy because you're not wasting the cellular machinery to make those eyes. We know that animals lose pigment because they don't need it to protect them against UV, and they don't need it to protect them and make them camouflaged against predators. So not having to make all that pigment is an energy saving. We find that microorganisms that live on the surface have mechanisms for repairing damage to their DNA that is caused by ultraviolet. With work that I've done with several colleagues, including Diana Northup at the University of New Mexico and her students, it's pretty clear that a lot of the subsurface microbes have dumped the ability to repair from UV damage. So, you know, they don't need it. And the other cool things that animals seem to do is not only have these physical changes, but also behavioral changes. So in some really classic studies that have been done, looking at a kind of animal species that is on the surface and a closely related species in a cave, when an animal on the surface tends to get hungry, they very often increase their level of activity and their breadth of search pattern for food, because that gives them a higher chance of acquiring food. But in a cave, you kind of have to wait for the food to come to you.
Right.
So it really isn't an advantage to get frantic and waste energy looking for food. And so a lot of the animals that are adapted to caves get more and more quiet and conserve energy. So it's a totally different strategy, even with closely related animals, because you're living in totally different environments. So I think it's a remarkable thing.
Well, yeah, it is remarkable how they adapt. Their whole life changes. Everything changes. I mean,
yeah.
they transform, if you will.
Yeah.
Here's a question for you. I'm going to read this slow. It says, Dr. Boston, if on Earth many of these microbes may see as being kept in check by the environment, could they perhaps be a thing that may restrict our forays into space or into spray, because it may be seen that they have no natural predators out there? Into space, not into
Sure,
space.
into space, yeah. And this is a really good question. And, we are really babies at the space game so far. But what we do know is whenever you change an environment, you certainly change the ecological relationships of organisms to each other. So, for example, even in a hospital, we have these infections that are called nosocomial infections, which means that you're much more likely to get them in a hospital than you are in your own home or a public building of some other different kind. And it's because, the built environment is so different. There's a concentration of ill people and so forth. And we certainly know that the space station and the Mir space station before it, and even some examples from Space Shuttle show that there can be overgrowth of human pathogens or organisms that are not usually pathogenic that might become opportunistically pathogenic when they're put in a different environment. And so the transformation of that little mini ecosystem that would be a spacecraft is profound, and we're only beginning to understand how those changes happen. And so in order for us to better manage how those happen, as we continue hopefully to send people into our solar system to explore, we'll have to learn how to manage those. But it's a very major effect.
Interesting. Very, very interesting. One question that somebody sent in, they mentioned a little comment about the notorious fireflies seen in space. I know in the movie The Right Stuff, I think it was whoever played John Glenn was talking about the little fireflies flying around the capsule. Do you think those were microbes that were getting ignited by friction, or what do you think? The one thing I've seen on many films about the ISS and Apollo and shuttle missions. Some people, say, well, look it's some sort of a UFO, it's some sort of spaceship. To me, it almost looks like some of them look like microbes moving around. Do you believe that's what they really are?
Well, I doubt it. I mean, the truth is that there's a huge amount of high-energy physics that goes on at low to mid-Earth orbit, which is, we think of it as a vacuum, but the truth is there's actually quite a lot of ionized gases in that environment. So I suspect that phenomenon is more akin to, something like noctilucent clouds, or any of these aspects of the physics of particles moving in this very low density and being subject to energy sources. I mean, that's hardly my field, but I think that microbes are probably an unlikely explanation for that. That being said, we don't actually know what those phenomena are, so we can always be surprised. But I suspect that it's more a situation that we don't understand the physics completely enough.
Yeah, I would kind of figure, and at the temperature there also, it's pretty cold. I would assume it would probably kill off just about anything that's known on Earth.
Well, cold doesn't really kill things off the way that heat does. So let me try to give the capsule version of what we understand about temperature. The way we regularly do long-term storage of bacteria and archaea is to essentially freeze dry them and then keep them in a minus 80 degrees centigrade freezer. If they are taken through that process correctly, then they're perfectly fine. So cold, depending on the kind of organism, can completely put that organism into what's known as a cryobiotic state. That is a cold, suspended, animation kind of state. It's not just microbes that can endure that. These cute little adorable guys called tardigrades or water bears or moss piglets, they're tiny little sub-millimeter size arthropods. And these are famous for being perhaps the toughest little buckaroos around, and you can bombard some of the species with incredibly high doses of ionizing radiation. You can completely freeze them down, and they go into this sort of spore-like form called a ton, and then get reanimated again. There are some of them that blow around in the Antarctic dry valleys for many years before they get a little bit of warmed snow occasionally in the summer, the Antarctic summer. So we know that at the cold end of the spectrum, organisms seem to be able to go down to extraordinarily low temperatures and be reanimatable and go on and live a happy life. And some of them are adapted to do this on a regular basis, not just the tardigrades, but also nematode worms in the Antarctic dry valleys, as a matter of fact. So the cold end of things, organisms seem to have strategies to cope with. The high end of things, you at some point come across the temperature threshold where the actual biomolecules that we're made out of actually have their bonds broken and they reconnect in a way that makes them not functional. This process is called denaturing. So the highest temperatures for which we have clear evidence is 122 degrees centigrade, which is well above the boiling point of water. And the only way that that can occur is if you have the system under pressure, so it suppresses the boiling. The physical act of boiling also does this denaturation process. We suspect that there are organisms that probably can live up to at least maybe 140, 150. Perhaps it has been claimed up to something like 200 degrees centigrade. Wow. But it's so difficult to work with those systems in the lab that no actual confirmation of that beyond 122.8 degrees has been shown in the lab. So while we all have suspicions that there are organisms living right in the necks and the throats of those deep-sea hydrothermal vents, living in perhaps the fringes of volcanic systems, at high temperatures, and certainly coming up with very hot fluids from below under certain geological circumstances, the actual proof is yet to be shown above this 122. I have to say 122 is gosh darn hot.
Yes.
So that's remarkable that there are organisms that seem to have been able to stabilize the stuff that they're made of at those temperatures, and yet they seem to have been able to do that.
Interesting. Terry writes in, this is Dr. Boston, with your cave, with all your cave experience, being that these are such dark places, but yet, this is a long email. I think what she's getting at is that there are some, even like at the bottoms of the ocean, there are animals, creatures, things, because I don't know the right term to use, Penny, that can generate light, that can create their own light. Have you come across stuff like that in these caves?
Yes, actually. There are different ways that this can manifest. So there's a passive property that things can have and be fluorescent when illuminated with ultraviolet. We certainly see that a lot of microbes are fluorescent when we look at them with either long-wave or short-wave UV. There are minerals, of course, that also are fluorescent under those conditions. That's somewhat of a passive process. It's something about the chemistry of their surfaces that have this fluorescent property. But there is also the other active biological process, which is known as bioluminescence.
Okay.
And bioluminescence actually takes energy, so an organism has to do something. So with deep sea fish, it's the combination of a compound known as luciferin and an enzyme that cleaves that called luciferase, because all enzymes end in ASE. And when those come together under the control of the organism, then you get bioluminescence. So things like deep sea fish that are perhaps trying to use these light flashes to either scare away predators or to attract potential prey, are actually, it's worth it to them to spend energy to do that. We have seen bioluminescent fungi actually in caves. And we believe that these are species that are unknown to science. I occasionally communicate with a fungus mushroom expert named Taylor Lockwood about these, and I would like to see more of them. I have also seen little flashes of what appear to be bioluminescence, but tiny little ones, and on wall surfaces, and we don't know who might be doing that or what the source of that is. So we think it's out there. It's a rare phenomenon. I have only seen it a few times, but the answer is yes. So I don't know why these fungi might be doing it, although I could speculate that if that were to lure lost insects from the outside, actually, to become near them, those insects might die in their vicinity. And when surface plants live in an environment where they can't get biologically available nitrogen, that's when you get these carnivorous plants that have mechanisms to eat insects. And so I'm wondering if it isn't an analogous purpose is being served with these subterranean fungi. But it's a curious thing.
I think it's interesting, especially these. You see these different programs. These little cuttlefish. Some of these cuttlefish that, of course, in like an octopus, it can change its color. But the cuttlefish can generate. I mean, almost like a laser. I mean, a super bright light. It's amazing that they can do something like that. I mean, it's miraculous, is what it is.
It is. It really is miraculous. And I've seen images of squid with propagating waves of light going down their sides and so forth.
Right.
I mean, really remarkable. There's certainly bioluminescence and fluorescence both in the jellyfish world as well. So there are a lot of organisms that have figured out how to do this, and the question is always to ask why. Why are they doing this? They must be getting something out of it. Organisms don't do stuff for no purpose because they have to get energy to live, and so whatever they do has to have a reason that's good enough for them to spend energy on it.
Right. Yeah, there's some just amazing creatures out there. What thing you talked about again in your bio? I'm just in the second part of the show. We want to talk about Mars, of course, but
sure.
But these acid waters, or these pools full of acid. Is that something that's pretty common in some of these caves? Is it the runoff or what is the rock expelling something?
Well, yeah. I mean, there's quite a few examples. If you look at the Earth as a whole, even though in any given part of the world they're pretty rare, and the usual mechanism in a natural cave for producing an acidic condition, a highly acidic condition, is the gas hydrogen sulfide. So there are many geological sources of hydrogen sulfide that are possible. And when that gas percolates into a cave, usually from deeper sources, and those sources can be associated with petroleum, or they can be associated with microbial or heat processes with minerals that contain sulfates. That gas is released, and it's very interested in combining with oxygen. And when hydrogen sulfide combines with a source of oxygen in water or in air, it produces sulfuric acid. And sulfuric acid is quite an aggressive acid compared to something mildly acidic like vinegar or something. And so that's really the acidic source that we have worked with primarily. Now, there are other acid systems that are attributable to acid mine drainage that also incorporate mobilization of iron, which is much more mobile in an acidic environment. The Rio Tinto in Spain is a classic example where it appears to be both a natural system but also exacerbated by probably 1,000 years or so of mining in that area. So whether it's a completely natural system and would be that way if it hadn't had this ancient and venerable history of mining, I don't know. But definitely there are a lot of sources, potential sources for acid in caves, and the acid itself, of course, can really break down bedrock like limestone-type bedrock or dolomite bedrock, and so the acid itself can contribute to the actual formation of caves of that sort.
So they actually it kind of etches it out, if you will?
It does. We know that acidic waters are very aggressive in dissolving out caves in limestone and dolomite. These are known as carbonates, right? So a lot of the caves on Earth are carbonates because we have a lot of carbonates on Earth and we have a lot of water. So a weak acid can be made just by dissolving CO2 from our air into rain and into groundwater. So rain is usually slightly acidic. Groundwaters can be slightly acidic or even, moderately acidic, but certainly not anywhere near as acidic as sulfuric acid. But the carbonic acid with the carbon dioxide is more than acid enough to gradually dissolve away carbonate caves. Now, caves made in other kinds of rock, different chemical system, different processes at work.
Interesting. Very, very interesting. Is there a lot of do you find when you do a lot of cave exploring that you find like natural springs and freshwater springs? Can you find a lot of fresh water there?
Sure. It depends on the overall amount of water in any given part of the world. So, if you are in the moist eastern United States, and you have systems where whole big streams and rivers flow through caves, there's a phenomenon known as sinking streams, which is very common in the kinds of landscapes where we find carbonate caves, where you actually have a surface stream that then drains into a hole, which is probably a collapsed former cave, flows for a while underground, sometimes reemerges again. This is very common. This kind of terrain is common in many parts of the eastern United States. We have some out here in the west. Very common in Europe. China has the biggest carbonate area in the world. This is a phenomenon that you find everywhere in the world. So some caves have huge rivers flowing through them. Some of the biggest caves in the world in different parts of Asia have these enormous rivers flowing through them. On the other end of the spectrum, of course, are the caves in deserts. And they moister than the surface by far. They often have, virtually saturated relative humidity. But the actual amount of flowing water through them is much less. You tend not to get rivers or streams flowing through them. You tend to get isolated pools. So it really is controlled by how much water is in the local terrain.
Right.
Is it a very rainy place or is it a very dry place?
Have you been in some of these caves, Penny, that are quite deep and just continue to drop and drop and drop?
I have been in quite a few deep ones, certainly not the deepest ones in the world. So right now, Kubera in the former Soviet state of Georgia is the deepest known cave in the world, and that's 2.2 kilometers of depth. And that is a high mountain system, so the system is extremely vertical. And teams from Ukraine and Italy, I think there have been some UK cavers, a few Americans, some French, over many, many years trying to push the leads on this cave, which means slowly making their way, many week-long expeditions. These caves tend to have clogs of giant boulders. You have to dive through freezing water to get to the next part of the passage. These are called sumps. So it's an extraordinary Olympic-style feat to actually do that kind of caving. The deepest cave that I have been in is one that I have studied for over 20 years, and this is La Chiguilla Cave here in New Mexico. It's the deepest cave in North America. so far known, and its deep point is about 500 meters.
Wow.
So, it's about 1,500 feet. And
Penny, we've got to take an NBC News break. Can we keep
Sure.
that for another go-around?
Yes, absolutely.
Okay, sounds good.